Here we are at one of ICI's plants for the manufacture of sulfuric acid by the contact process. And here we are at an ICI plant for the manufacture of ammonia by the Haber process. Both of these very important industrial processes use catalysts to speed up the rates of reaction. And the catalysts in both cases contain the transition elements. Welcome to the colourful world of the transition elements. In this programme we're going to see the general characteristics of the transition elements, and then we're going to see reactions of transition metal ions in aqueous solution. And we're going to characterise these reactions so that you can understand the system of inorganic chemistry. First of all, we've got to ask ourselves, what is a transition element? Here, the periodic table of the elements, we see the S block elements here in groups 1A and 2A, where the S orbitals are being filled with electrons. We see the P block group of elements, where the P orbitals are being filled with electrons, and here, right in the middle, is the D block elements, where the D orbitals are being filled with electrons. The most usual definition of a transition element is that it's an element which has the configuration D1 to D9 either in the metal itself or in one of its common oxidation states. So the transition elements start with scandium, which has the configuration 3D1 4S2. So it has the D1 configuration in the metal and is therefore a transition element. Let's now look at copper and zinc. Copper has the configuration 3D10 4S1, and in its common ion it has the configuration 3D9. So copper is a transition element. Zinc, on the other hand, has the configuration 3D10 4S2 in the element, and in its common ion, zinc 2+, it has the configuration 3D10. So in neither the metal nor its common ion does it have the D1 to D9 configuration that we require of a transition element. Let's look at the general characteristics of the transition elements. They form coloured ions. They're often paramagnetic and sometimes have very unusual magnetic properties. They show variable oxidation states. They're often useful as catalysts, and they form a wide variety of complex compounds. Where do these colours come from? Colour comes from electronic transitions between energy levels. When a system gains energy delta E by absorbing radiation of frequency nu, the transition can occur. In our equation, delta E equals h nu, h is Planck's constant. Two types of transition can occur. When both the energy levels are d electron energy levels, then we say a dd transition occurs and we get weak colours. When, however, one of the energy levels is a metal orbital and one corresponds to a ligand orbital, we get charge transfer colours. Here we have the copper 2+ ion, here the cobalt, here nickel, and here chromium 3+. And these are examples of DD colours. And here we have the manganate 7 ion and the dichromate 6 ion. And these ions have no d electrons in them, they're d0 systems, and their colour arises from charge transfer transitions. Let's now look at the magnetic properties of transition metal compounds. You'll have all seen a piece of iron jump onto a magnet, and that's ferromagnetism. That's an extreme example of a property that we call paramagnetism. Paramagnetic materials are those materials which are attracted into a strong magnetic field. Chemicals like copper sulfate and iron sulfate and cobalt chloride, these are all paramagnetic. They are actually attracted towards a magnetic field. And the property of paramagnetism comes from the possession by the metal ions of unpaired electrons. The opposite of paramagnetism, that is, something which is repelled by a magnetic field, is called diamagnetism. And diamagnetism is a property of all systems that contain paired electrons. Now, supposing we have something which is perfectly diamagnetic, that is, it repels materials. Shouldn't we then be able to repel a material and levitate it against the force of gravity? And that's what we can do with a pellet of superconducting material. This pellet that we have here is made of yttrium-barium cuprate. It contains copper in two oxidation states, +2 and +3. And at the temperature of liquid nitrogen, minus 196 degrees centigrade, this pellet will become superconducting. And sitting on top of the pellet, I have a little magnet. If I pour liquid nitrogen in now to the dish and cool the pellet down, at minus 196, it will become perfectly diamagnetic, it will repel the magnet, and the magnet will rise up and hold itself in a position where the force of repulsion by the superconducting pellet balances the force due to gravity. So let's now put liquid nitrogen in and see if we can see the levitation effect. And now we can see that the magnet has been levitated. In a short while, as the superconducting pellet warms up, as the liquid nitrogen level drops, the pellet will no longer become superconducting and the magnet will drop back down to its rest position. Now we come to the variation in oxidation state shown by the transition elements. Here in front of me are the common oxidation states shown by chromium. We have potassium dichromate 6, chromium 3+ AQ and chromium 2+ AQ. The formulae of the species present in these solutions are shown. You see that the dichromate 6 species is a D0 system, so its colour arises not from a DD transition, but from a charge transfer transition. Chromium 3+ AQ contains the hexaaqua chromium 3+ ion, and you'll notice that's not green, but it's ruby coloured, the same as in hydrated chromium 3 sulfate or chrome alum. And chromium 2+ is stored under hydrogen because it's very easily oxidized in air, and this is the blue solution, the blue chromium 2 aqua ion. We're going to investigate this sequence now by doing this experiment, in which I have potassium dichromate 6 in the flask with water and granulated zinc. I'm going to add hydrochloric acid dilute to this flask so that the zinc will begin to dissolve and produce electrons to carry out the reduction of the dichromate 6. The orange colour then is the dichromate 6, and after the acid has been added, you'll notice that air is being displaced, and so the atmosphere of hydrogen which is being produced is going to preserve the solution from oxidation by atmospheric oxygen. And just keep the acid going in until we're sure that the zinc is adequately dissolving. Now we can in about 5 minutes' time, the solution will change from orange as the zinc reduces it, and we will have a green solution in there, which will be a solution of chromium 3+, in which 2 of the water ligands are replaced by chloride ions. And so the species present in there will be the dichloro tetraaqua chromium 3+. While this experiment is going on, perhaps we could have a look at the species that are actually present in the solution. You see that the chromium 3+ ion will be green because of the chloride ion coordination and not the colour of the hexaqua ion that we had earlier. Now you can see that we've reached the green chromium 3+ stage, and we should take now probably another 5 or 10 minutes before this green colour is converted into a blue colour of the chromium 2+ ion. And we can see that now the chromium solution has gone blue. We have chromium 2+ present, and what I'm going to do is force the chromium 2 solution over under the atmosphere of hydrogen, which is protecting it, into this solution here of sodium ethanoate. And when the chromium 2 solution hits the ethanoate solution, we shall see the red colour due to the dimeric chromium 2 ethanoate being precipitated. So I'll just tighten up this valve here to stop the hydrogen bubbling out so as to create a pressure inside the flask, and the blue solution will then go over and we produce the red colour, which is chromium 2 ethanoate, which will slowly precipitate and produce us a relatively stable chromium 2 species. If I stop the reaction at this stage, because I want you to see what will happen if we let oxygen into here, if I remove this bung, and we must note carefully the colour of this solution, which remember is protected by hydrogen, and what you see, something back in there, is that the blue solution turns green as I shake it in oxygen. So that even though zinc is present in excess, oxygen is getting in there and oxidizing the chromium back to chromium 3. But of course I could leave that connected and it would reduce down again. The structure of chromium 2 ethanoate is a metal-metal bonded structure, and rather famous because it was one of the first quadruply bonded metal-metal bonded species studied. Now let's look at the oxidation states of vanadium. At the start of the program we saw sulfuric acid being made by the contact process, and in this process vanadium pentoxide is the catalyst which oxidizes sulfur dioxide to sulfur trioxide. In the process you see that the vanadium is reduced to vanadium 4 oxide and then oxidized again by oxygen to vanadium pentoxide, so that the vanadium is acting as a catalyst, and the overall equation is sulfur dioxide being converted to sulfur trioxide. We can have a look at the oxidation states of vanadium in the laboratory in much the same way as we did with chromium. I have zinc covered with water, and I'm going to add some ammonium vanadate 5. There we go. So there we have vanadium in the 5+ oxidation state, and in the presence of a little acid, that will assume the orange colour. There's the orange colour of the VO2+ ion. I'm now going to add more acid so that the zinc begins to dissolve and we begin the reduction process. You can see that as the zinc begins to dissolve, the colour is changing from orange to a green colour, which is a mixture of orange and blue, because in a few moments' time this solution will be blue. I'll cover it loosely with a cork to let the hydrogen out, but to keep some air from going in and oxidizing the vanadium solutions. You see there that the first colour that we're going to see after the orange is the colour of the oxovanadium 4 ion, VOH2O5 2+, and that's blue, and you can see that that solution, that blue colour, is developing there now. So that's the blue colour associated with vanadium 4. As the reduction proceeds, it will go to the violet blue colour of the hexaqua ion of vanadium 3+. But if we have a high concentration of chloride ion, then just as we had with chromium, we shall have a green colour because we shall have chloride ions substituted into the coordination sphere. So we'll leave that experiment going. It's now in the vanadium 4 state. I'll leave it corked and we'll observe that in a few moments' time. Now if we return to the vanadium solution, you see that it's in the blue-violet stage of vanadium 3+. So I obviously haven't got too many chloride ions there to make it go green, but we keep the cork reasonably tight with just a little air hole, and in a few minutes' time we should have managed to convert it into the lilac-coloured vanadium 2+ hexaaqua ion. We can now see that the vanadium has been reduced to the vanadium 2+ state, because now we have the lilac colour of the hexaaqua vanadium 2+ ion, which is protected by the atmosphere of hydrogen above it, which is coming from the zinc and acid. So we have reduced vanadium 5 all the way down to vanadium 2 with zinc and acid. Now we come to our fourth property that we mentioned as a general characteristic of the transition elements, and it's one of the most important. This is the property of catalysis. We've just seen how vanadium pentoxide is an important catalyst in the sulfuric acid process. And that process, as well as the Haber process, which uses an activated iron catalyst, are examples of heterogeneous catalysis. That is, the catalyst is in a different phase to the reactants. But there are many homogeneously catalyzed reactions shown by the transition metal ions. And I just have one here to show you. We have a solution of ammonium persulfate dissolved in concentrated ammonia in the flask, and I'm just going to put some in this larger flask. This solution is unstable. The persulfate ions want to oxidize ammonia to nitrogen, and they just need a catalyst, a transition metal, which can show a variable oxidation state. And if I had a drop of silver nitrate, the silver ions will be oxidized to silver 2+, which will then oxidize the ammonium ions to nitrogen and itself be reduced again to silver 1. So here's a little drop of silver nitrate going into this unstable situation. And we see that the reaction builds up as the catalyst gets to work and increases the rate of the reaction so that all of the ammonia is converted into nitrogen very rapidly. That's an example of homogeneous catalysis shown by a transition metal ion. Our last but most important characteristic of the transition metals was that they form a wide variety of complex compounds, and we've already seen some of these in the experiments we've done so far. In a complex compound, the metal ion is bonded to other ions or molecules which are called ligands. And these ligands possess lone pairs of electrons. And these lone pairs of electrons are donated into empty orbitals in the metal complex. The term ligand means the same as Lewis base or nucleophile. So nucleophiles, Lewis bases and ligands are electron pair donors. It's very important to realize, therefore, that when we're working with transition metal ions in aqueous solution, we're working in a solvent which is a ligand. Water is a ligand, it's a Lewis base, it's a weak nucleophile. And so we can't work in aqueous solution with a bare transition metal ion. We always have an aqua complex. If we look at chemicals that you have on the laboratory shelf, here are just 3 transition metal salts. This first one is iron 3 ammonium alum, ferric alum, and you can see it's pale violet, so that the colour of the iron 3+ aqueous ion is not brown, it's violet. The X-ray crystallographers tell us that this salt contains the hexaaqua iron 3+ ion. And here is chromium 3 sulfate hydrate again, which we already know contains CrH2O6 3+. And here is cobalt chloride. Or is it? No, this is cobalt chloride hydrate. In this species, the cobalt again is surrounded by 6 water molecules. So these what we thought were simple salts are actually complex compounds, because the metal is bonded to 6 water molecules and not to the anion present in the species. And we define in a coarse way a complex compound as one in which the coordination number of the metal exceeds the oxidation state. In all of these species, the coordination number of the metal, that is the number of next nearest neighbours, is 6. And yet the oxidation state is 3, 3 and 2. And so these are all complex compounds. This is cobalt chloride, which is blue. This hasn't got any water. And this is cobalt bromide, which is green. These are anhydrous salts. You'll probably have seen water being added to anhydrous copper 2 sulfate, and the white anhydrous salt turns blue. Well, let's do it with anhydrous cobalt salts. That's cobalt chloride, and this is cobalt bromide. And if we add water to these, you'll see what will happen. There is a reaction. The water reacts with the cobalt salts and produces the hexaaqua cobalt 2+ ion, and both of these are dissolving to give pink solutions from which we could isolate cobalt chloride hydrate, cobalt bromide hydrate, and they would look very similar because they contain, just as this sample does, 6 water molecules bonded to the metal. We can see the coordination number exceeds the oxidation state, and we draw the arrow to show that the water is bonded to the cobalt via a coordinate bond. And a coordinate bond is a covalent bond, but it just denotes, the arrowhead denotes, that the pair of electrons in the bond originally came from the oxygen atom and are being donated to an empty orbital on the cobalt complex. The realization that in aqueous solution we are dealing with a hexaaqua ion, and the reactions of this ion enables us to understand inorganic chemistry in aqueous solution, and further it enables us to predict reaction chemistry, and that's what we're going to see now. Here is a model of the hexaaqua ion. In this model, the black ball represents the metal ion and the white balls represent the oxygen atoms of water molecules. And you can see that in this structure all the bond lengths are the same and all the bond angles are 90 degrees. This is the octahedral structure. It's the commonest structure in inorganic chemistry, and it's extremely symmetrical. Here is a diagram of the structure of the hexaaqua ion, and what I want you to notice in this structure is that there are only 2 types of bond. There is bonds of type 1 in which the oxygen is bonded to the hydrogen, and bonds type 2 in which the oxygen is bonded to the metal. And when chemical reactions occur, we must break bonds and form new bonds. And if bonds of type 1 break, then hydrogen comes off as H+, and so we call this the acidity reaction. If bonds type 2 break, then we call this the substitution reaction, because we're replacing the water molecule with a different ligand. So the 2 types of reactions that metal ions show are the acidity or the hydrolysis reaction and the substitution reaction. It's a nucleophilic substitution reaction because we are displacing one nucleophile by a stronger nucleophile. And we're now going to look at both of these reactions and to see these reactions occurring so that we can understand the system of inorganic chemistry. The first reaction we'll look at then is the acidity or hydrolysis reaction. In this reaction, you can see what happens is that a water molecule which lies outside of the immediate coordination sphere of the metal aqua ion has the choice to bond either to another water molecule in the solvent water through hydrogen bonding, or to bond to a hydrogen atom which is bonded to the oxygen which is bonded to the metal. And the delta plus delta minus charges there show you the attraction, electrostatic attraction, that's formed between the water molecule and the coordinated water molecule. And if that bond that forms there is strong enough and forms a strong bond, then the OH bond breaks, and so that on the right-hand side of the equation you can see what has happened is that H3O plus has been produced, which is the Lowry-Bronsted acid in aqueous solution. And we're left with an OH bond bonded to the metal, a metal hydroxide. So the equation that's important is written at the bottom there, and you can see that for metal 3 plus ion, an equilibrium is established, producing a metal hydroxide complex and H3O plus. Now, let's have a look at a reaction when M is Fe3 plus. I have in front of me the iron 3 alum that we've seen before, which is a pale violet colour. And now I'm going to add water to it, and we're going to see what happens. The pale violet, almost colourless crystals will slowly dissolve to form a brown solution. So we know that a reaction has gone on because we had pale violet crystals and they've dissolved to give a brown solution which obviously contains some new species. And the new species is the iron hydroxo complex. If we wanted just to have the hexa-aqua iron 3 plus ion there, we could get it by adding H3O plus to the equilibrium which has been established and forcing the equilibrium back over to the left-hand side. Let's just add some concentrated nitric acid, which is a strong but non-complexing acid, and you can see what happens. The brown colour disappears as the monohydroxy species is reconverted into the hexa-aqua ion. Well, let's show the other product of the reaction. Let's do the reaction again. We're adding water to the iron alum which contains the hexa-aqua ion. The hydrolysis reaction is taking place and forming the brown hydroxo complex, and now I'll just add some indicator to show you that there are some H3O plus ions there. This indicator is red in the presence of acid, and you can see that that solution is acidic, and so we have shown the presence of both the hydroxide complex and the acidity by adding reagents to this system. There we have the species present in the solution. The violet hexa-aqua ion has been converted into the brown ion and H3O plus. But it's important to realize that the equilibrium lies well to the left-hand side, and so that there are far more hexa-aqua ions present than there are H3O plus ions in the solution. The iron solution is a weak acid, about as strong as ethanoic acid. That is, its pK is around 3. Let's look at a reaction of acidity then. Supposing we had to predict what would happen if we treated a solution of iron 3 sulfate with sodium carbonate. What we have to realize is that sodium carbonate is the salt of a weak acid, carbonic acid, and the metal iron is a stronger acid than carbonic acid. And so if we treat a metal 3 plus salt with sodium carbonate, we shall get effervescence of carbon dioxide, and the metal hydroxide will precipitate. Let's do that. Here I have a solution of iron 3 sulfate, which is brown because of the hydrolysis reaction. And we'll add some sodium carbonate, solid sodium carbonate, to the solution and see what we observe. And I think you can see that there's effervescence in there and a brown precipitate is forming. So the effervescence is coming because there were H3O plus ions there which are attacking the carbonate. Here is chromium 3 plus AQ from chromium 3 sulfate, and we'll add sodium carbonate here, and we shall get effervescence. You can see it effervescing now, and a green precipitate again of the metal hydroxide. These reactions are shown. The carbonate removes H3O plus ions from the equilibrium, and so sending the equilibrium over to the right-hand side. We can use Le Chatelier's principle to explain this, or just the equilibrium law, that the equilibrium constant will maintain itself. And if we remove H3O+, then the mixture will re-equilibrate to produce more H3O+. And what you can see is that once one stage of the hydrolysis has occurred and gone to completion, then two more stages of hydrolysis can occur until we get the brown precipitate, which is iron 3 hydroxide, which I have written as FeOH3 3H2O. And exactly the same thing happened in the chromium solution. It's not just carbonates that we can't make in aqueous solution. We also can't make sulfites or thiosulfates or sulfides or nitrites or ethanoates, because these are all derived from weaker acids than the metal aqua ion. So metal 3+ ions do not form carbonates in aqueous solution. And of course, metal 4+ ions are even more acidic, and so we don't get any of those salts with metal 4+ ions either. The complete equilibria are shown. For the metal 3+ ion, there are the three stages, and pK, which is minus log 10 K, is approximately 3 for that system. So these are weak acids, but stronger than carbonic and sulfurous, and so on. For 2+ ion, the equilibria are as shown. There are only two stages of the hydrolysis, and the equilibria now lie very much towards the left-hand side, so that the 2+ ion is not very acidic, and the pKa for the system is about 8. That is, the equilibrium constant is K is around 10 to the minus 8, and so very much lower acidity than in the 3+ ions. So what we're seeing is that metal 4+ ions are extremely acidic, metal 3+ ions are acidic, and metal 2+ ions are very weakly acidic. Let's look now at the addition of strong alkalis to transition metal salt solutions. The addition of ammonia or sodium hydroxide, which are stronger bases than sodium carbonate, invariably result in the precipitation of transition metal hydroxides, because the first thing that they do is to remove the H3O+ ions in those equilibria that we've been looking at and push the equilibrium over to the right-hand side. So we can write the equations as shown. Here we have copper 2+ in aqueous solution. This is a solution of copper sulfate. But remember that it doesn't contain any CuSO4. What it contains is CuH2O6 2+. And what will happen if we add sodium hydroxide solution? Well, we shall immediately attack H3O+ ions and cause the formation of a blue precipitate of copper 2 hydroxide. There's our blue precipitate of copper 2 hydroxide, formed by the hydrolysis reaction being forced to the right-hand side by removing the H3O+ ions. But supposing we added the hexaaqua copper 2 ion to the sodium hydroxide, so that now the hydroxide ions are in vast excess. Let's see what happens. And what happens now is that we get a deep blue solution. There is no precipitate now. We say the copper hydroxide is amphoteric. Not only will it dissolve if I add acid, but it will dissolve if I add alkali. And we can see the scheme for amphoterism as shown. That is, metal 2+ hydroxides dissolve to form metallates, and the examples there are zincate and this one here, which is cuprate. The ending 8 means that the metal is in the anion. It has a double negative charge. So this is cuprate and this is copper hydroxide. And for 3+ ions, you can see that we get things like aluminate, and we also get in the transition metals, we get chromate and so on. So amphoterism is a characteristic property of transition metal hydroxides because they are transitional. They're transitional between the very basic hydroxides on the left-hand side of the periodic table and the very acidic hydroxides on the right-hand side of the periodic table. So in the middle we have the amphoteric hydroxides that dissolve in both acidic and basic media. Now let's look at the substitution reaction. Remember that in the substitution reaction what's happening is that we're replacing a water molecule by another nucleophile. There are two types of nucleophiles or ligands that we can use, either neutral ones, that's ligands that don't have a charge, or anionic ones, ligands that have a negative charge. So let's look first of all at the general equation for a substitution reaction by a neutral ligand. I've written L as a ligand there, and you can see that the nucleophilic substitution reaction is a reaction of replacement. We are replacing the water molecule by the new ligand. Well, the commonest ligand, which is neutral, is ammonia. So let's see what happens when we add ammonia to transition metal salt solutions. Now, first of all, we should realize that in the equation that we had, only one ligand was replacing one water molecule. But if we use an excessive ligand, then we can replace more water molecules. This reaction scheme looks very complicated, but actually it's very simple. In each reaction, we're replacing a water molecule with an ammonia molecule. And because there are 6 water molecules, there are 6 stages. So we start with a metal hexaaqua ion, and we end up with a metal hexaamine. You'll notice that when water is coordinated, we call it aqua, and when ammonia is coordinated, we call it amine. Those reactions look very complicated, but they're really very simple. You just keep substituting one water molecule for ammonia. So let's see how those reactions proceed with 4 transition metal ions that I have in front of me. The first ion that I have here is nickel 2+. This is hexaqua nickel 2+ made by dissolving, this was nickel nitrate in water. And I'm going to add ammonia. What's the first thing that we shall see? If I add a little ammonia, what happens is that we get a precipitate. And that isn't in our scheme of ammonia complexes or amines. And haven't we forgotten something? This is nickel hydroxide. You remember that if we add ammonia to any transition metal salt solution, we shall precipitate, first of all, the metal hydroxide. All the transition metal hydroxides are insoluble in water. But what happens now if we add excess ammonia? Then we shall dissolve the hydroxide and form an amine. And now in that solution we have nickel hexaamine. The nickel ions are now surrounded by 6 ammonia molecules, and if we wished we could isolate this hexaamine as the bromide salt. If we added sodium bromide solution to that, down would come the violet crystals of hexamine nickel 2 bromide. Our next solution here is chromium 3+, the ruby colour of chromium 3 sulfate. What will happen when we add ammonia to chromium 3 sulfate? We shall see a precipitate of chromium hydroxide. What will happen when we add excess ammonia? The chromium 3 hydroxide will dissolve to form a hexaamine. Now you say, it's not dissolving. Well, we'll have to leave it for 5 minutes. Chromium 3+ is a peculiar metal in that it has a D3 configuration and its reactions tend to be slow. You might be used to organic reactions taking a little while to go, and chromium 3 is a little bit like those. You can begin to see now that that green precipitate is dissolving to form a violet solution. And it's the violet solution of the 6 ammonia complex, the hexaamine. We'll come back to it as the reaction proceeds. Here is copper sulfate solution, which of course is hexaaqua copper 2 plus. What will happen when we add ammonia? First of all, we shall see a precipitate of copper hydroxide. There is a precipitate of copper hydroxide, and what will happen when we add excess ammonia? The hydroxide will dissolve to form a deep blue violet solution. There it is, and that solution is a rather famous solution. It's been used for making artificial silk by dissolving wood cellulose and extracting it as a fibre. And it's also a very important solution for making industrial copper catalysts. But the difference is that now we have a D9 electronic configuration in copper, and this particular solution contains the tetraamine bis aqua complex. If we look at our scheme again, what has happened in this solution is that we have reached the stage 4, that is, the equilibrium has stopped when 4 ammonias and 2 waters are coordinated to the copper. And this is because copper is a D9 electronic configuration, and the structure is actually a distorted octahedron. It's distorted because of a thing called the Jahn-Teller effect. But you can imagine it as just the equilibrium position reached in 880 ammonia. This is concentrated aqueous ammonia, and of course in here we have more water than we have ammonia. If I bubbled ammonia gas into this solution and cooled it down in ice, then we should get the pentaamine, the 5-ammonia complex. And in liquid ammonia, we can get the hexaamine. So it's not that those compounds are unstable, but in aqueous solution, water and ammonia is competing. They're both competing for the sites on the copper, and in this concentration, water is winning for 2 of the sites. Now let's add ammonia to cobalt 2 plus AQ. And this is perhaps one of the most famous experiments in the whole of coordination chemistry, because what we're going to be producing in here are the very famous cobaltamines. So let's first of all add ammonia, and what will we see? We shall see a precipitate of cobalt hydroxide. Now I'm going to carefully add excess ammonia down the side of the tube, and you'll see what happens. The cobalt hydroxide dissolves, and we get a brown solution. It's a pale brown solution. And I'm just stirring it gently to make the cobalt hydroxide dissolve in the excess of ammonia. It's a straw-coloured solution. Now I'm going to remove the bung from this solution. This solution contains cobalt hexaamine, cobalt 2 plus hexaamine, and now we're removing the bung, and I'm going to shake it so that oxygen is admitted through the top. And what we see is the longer that I allow oxygen to go in, the darker the colour of the cobalt solution becomes. And over a period of 5 or 10 minutes, this will become really dark. I'm shaking in oxygen from the air to allow the cobalt to oxidize to cobalt 3. So unlike these other elements, cobalt has a higher oxidation state, which is easily reached in alkaline solution. And here we're making the cobaltamines. It was in 1891 that Alfred Werner published his first paper on the cobaltamines at the age of 25. 22 years later, he received the Nobel Prize for Chemistry. And what Werner did was to sort out the chemistry going on in this process. If we have a look at the scheme, so that we can see in the scheme that the pink cobalt ion, first of all, it became the cobalt hydroxide, which dissolved in excess of ammonia to give the hexamine cobalt 2 plus ion, which was a pale straw colour. And then, as we admitted oxygen, it went to a dark brown mixture. Now, the principal species present in the mixture is the hexamine cobalt 3+ ion, and this species is yellow. But the brown colour derives from the fact that we have a mixture of species in there. We have the aqua pentamine, which is purple, and we have the chloropentamine, and that's also purple, as well as other species. So it's the mixture of purple and yellow compounds in there that give it this brown colour. Alfred Werner was able to look at the chemical formulae that you see listed there of cobalt-3 chloride with different numbers of ammonia molecules and come to the conclusion that in all of those 4 compounds, cobalt had the same 2 valencies. He called them primary and secondary valencies, but we now call them oxidation state and coordination number. In each compound, you see the cobalt has an oxidation state of +3 and a coordination number of 6. We can now see that the chromium-3 hydroxide has completely dissolved, and we have the chromium-3 hexamine species present in that solution. We can see on the scheme that chromium-3+ gives a precipitate of the hydroxide whether we add ammonia, sodium hydroxide or sodium carbonate solution, and this green hydroxide will dissolve in ammonia to form the violet-purple hexamine. And it will also dissolve in sodium hydroxide because, like the copper hydroxide, it's amphoteric and we form a chromate. And it's that chromate solution which is readily oxidized under the presence of the alkali by hydrogen peroxide to our chromate 6, which becomes dichromate 6 if we acidify. So in each of these reactions, what we've seen has been the formation of metal amines. Hexamines are the rule, and the exception is the copper complex. And the copper complex, we said, is the tetraamine diaqua complex, shown on the scheme. And it's important for us to write that species with the 2 water molecules in, rather than writing it as CuNH3 2+, because that species we might imagine to be tetrahedral. But we know the structure of this ion. The 4 ammonia molecules are in the plane, and there are 2 water molecules a little bit further away from the copper in the axial bond positions. So what we've seen in these reactions is that if we take a neutral, uncharged ligand about the same size as a water molecule, we don't get any change in coordination number. Occasionally, we get a change in oxidation state, as we saw in the cobalt case. But we don't go from octahedral to tetrahedral or to any other shape if we keep the ligand the same size as water and with the same charge. But what we're going to see next is what happens if we use an anion, a charged ligand, which is larger than a water molecule. A concentrated solution of chloride ions is to be found in concentrated hydrochloric acid. So I shall use that as my solution of chloride ions that we're going to add to transition metal aqua ions. This first experiment that I'm going to do is one that was done in these laboratories by Donnan and Bassett in 1902. We take a pink cobalt solution and we add concentrated hydrochloric acid. And we see what happens. The pink solution turns blue. And the excitement in this experiment, in those long-distant days, was that Donnan and Bassett showed that there's no change in oxidation state of the cobalt. They showed that there's merely a change in the coordination number. And at that time, colour was thought to be arising out of a change in oxidation state. So we now know that colour can arise from change in oxidation state and a change in coordination number and a change in the ligand. So here, the cobalt has gone from pink to blue, and if we dilute the solution with water, we see that we get the pink colour back. So there's obviously an equilibrium present in that solution. In the pink solution, we have the octahedral hexaaqua complex. And in the blue solution, we now have a tetrahedral species. And Donnan and Bassett were able to show that this change had occurred by putting electrodes into the apparatus and finding that the blue species went to the positively charged electrode, and therefore that the blue species was anionic. And they correctly formulated it as COCl4 2-. Now what's remarkable about this is that not only is there no change in oxidation state, but not only does this work for cobalt, but it works for very nearly all metal 2+ ions. So let's have a look at some other reactions. Here is copper 2+ AQ, and let's see what happens when we add chloride ions to copper 2+ AQ. The colour changes from blue to this olive green colour, and in that solution we now have the tetrachlorocuprate. And so we can write a general equation for the reaction that's occurring with metal 2+ ions. A change of shape occurs then, the metal going from octahedral to tetrahedral in the presence of the larger anionic chloride ions. So it's the size and the negative charge, that the fact that the ligands are repelling each other and that it's not a low energy situation to cluster 6 chloride ions around a metal 2+ ion, that dominates in this change of shape. You can see that with a metal 3+ ion, with excessive chloride ions, again we can get a tetrahedral MCl4- species. But you need a lot of chloride ion to do that. And we have seen in chromium chemistry earlier that you tend to retain the octahedral stereochemistry when you put just 2 chloride ions around the chromium with 4 water molecules. But here is the iron 3 situation again, iron 3 sulfate, brown in water because of hydrolysis. If I take the brown colour away with nitric acid to get the hexaaqua ion, and there we are, now we've got the hexaaqua iron 3+ ion present in the solution. It's very pale violet so that the solution looks colourless. But now if I add chloride ions and we get a tetrahedral complex, we see a colour change and we get the tetrachloroferrate 3 ion. And you'll have met probably the tetrachloroaluminate ion in organic chemistry in Friedel-Crafts catalysis, where AlCl3 becomes AlCl4- by capturing a chloride ion. So this is a general reaction of metal 2+ and metal 3+ ions, dominated by the size and charge of chloride. And of course, if we take bromide or iodide, then again, we're even more likely to get tetrahedral complexes. So can we ever get octahedral complexes of metal 2+ and 3+ ions? Yes, we can. And we can see that octahedral complexes occur if we take a smaller anion. Fluoride ion is smaller than chloride ion, and we can pack 6 fluorides around a metal 3+. And Na3AlF6, the octahedral complex of aluminium, is very important as cryolite in the manufacture of aluminium. And iron forms a similar complex, FeF6 3-. We can also put 6 chlorides around a metal if we have a 4+ charge on the metal. And you can see that if we take titanium 4+, then we can put 6 chloride ions around it because the greater charge on the metal manages to hold them electrostatically together, and so that the repulsive effect is counterbalanced by the attractive effect of the 4+ charge. So what we've seen so far has been that metal ions form octahedral complexes with ammonia, but with chloride ions they tend to form tetrahedral complexes. All of the complexes we've seen have either been octahedral or tetrahedral, and those are the commonest shapes in inorganic chemistry. But sometimes we get different shapes, and I thought we'd end by seeing a different shape, and one which occurs with metal ions of D10 configuration. Ag+, that's silver ions, and Cu+, copper 1 ions, have the configuration D10. And these ions very much prefer a linear geometry in their complexes, so that we only get two ligands bonded to the metal ion. Now let's have a look at the reaction of silver nitrate with hydrochloric acid to exemplify this. If I put silver nitrate into the flask, and to the silver nitrate solution I add hydrochloric acid, I get a white precipitate of silver chloride. But supposing I have an excess of chloride ions. Supposing I put hydrochloric acid into this flask and I add silver nitrate. Will I see a precipitate? I see a transient precipitate, but the precipitate dissolves in excess of the hydrochloric acid. In other words, the silver nitrate solution precipitates silver chloride, but because there are excess chloride ions present, then coordination occurs, and just as we saw with ammonia, the presence of an excess of ligand causes an ionic species to be formed, which will then dissolve in the aqueous solution. And we can see this equation. The silver chloride is forming AgCl2- ions, which are linear, all in a straight line. And you'll be aware that if I add ammonia to this solution, the silver chloride will dissolve to form the bis amine of silver plus, which is known as Tollen's reagent, which we use in organic chemistry to distinguish between aldehydes and ketones. And that again is a linear complex of silver. And those who do photography will know that silver bromide dissolves in hypo sodium thiosulfate, and that again forms a linear thiosulfato complex of silver. We've seen octahedral complexes, tetrahedral complexes, and linear complexes. And the only other common shape is square planar. And square planar complexes occur with metal ions of configuration D8, and that is nickel 2+. And nickel 2+ forms a square planar complex with butanedione dioxime, or dimethylglyoxime, and this carmine red precipitate that we get is used in the gravimetric estimation of nickel, and it's also used as a colour qualitative test for nickel. Nickel similarly forms a square planar complex with cyanide ions, NiCN4 2-. So they're much rarer, but they do occur. In conclusion, I would like just to go down out of the first row transition elements, where we've seen a lot of pretty chemistry, and we've seen some of the uses of transition metal species in catalysis. But what about uses outside of catalysis? We've been using the ligands ammonia and chloride ion, and it might seem all very irrelevant to other fields such as medicine. But no, if we go down to the third row and we use ammonia and chloride ions as ligands to platinum, we get this compound. And because platinum 2+ has the configuration D8, it forms square planar complexes like nickel 2+. This compound, cisplatin, is a square planar complex containing platinum 2+ bonded to chloride ions and ammonia molecules. And this is an inorganic anti-cancer agent. This drug and its more recent derivatives are extremely effective in the treatment of certain types of cancer.